In the last video, we learned how you can use the Stefan-Boltzmann law to calculate the temperature of an object if you know the amount of energy that an object is radiating. Now we're going to use that information to think a little bit about how the greenhouse effect might work. To do that, we're going to create a simple model of the heat balance of the Earth and then slowly add complexity to that model to bring it more in line with reality. The driving question that we're going to ask in each of our models is, what is the temperature at the surface? The key insight that will allow us to construct these models is to realize that the Earth system is more or less at steady state. At any given time, the planet is, on average, emitting as much energy out to space as it absorbs. How do we know that? Well, imagine for a minute that it was constantly emitting a little more energy than it absorbed. That would mean that there was a net energy going out relative to energy coming in, and if there's net energy leaving the planet, then it would be cooling down. If that kept up for a long time, then eventually everything's going to freeze over, even the air. On the other hand, if you absorb more energy than you emit, then you'll warm up. So if there's more going in than going out, then it's going to warm up. And if the planet keeps heating up and heating up and heating up without any stop, then eventually it will explode. The planet comes to steady state because emissions are a function of temperature. So when incoming radiation decreases a little, the planet cools down a little, and that reduces the outgoing emissions until they're back equal to the incoming emissions at the slightly lower temperature. That's steady state. Now, you might say, wait, I thought the Earth was heating up. Isn't that what global warming's all about? Well, yes. But given the huge amount of energy that hits and leaves the planet, almost 200,000 terawatts all the time, the actual imbalance is a tiny rounding error in the equation. So what we'll say is that in the short term, temperature isn't changing, and we'll do calculations with that in mind. It turns out that the idea of doing calculations based upon a steady state assumption is extremely useful in science, and you'll use it over and over if you haven't already, so let's give it a shot. Let's start with the simplest model possible. What if the Earth were a little rock floating around in space with no atmosphere? What would its temperature be? Well, let's say we know nothing about the Earth except where it is in space and how much energy it reflects away. The amount of energy that a planet reflects or otherwise does not absorb is called its albedo. What we're going to try to do is figure out how much energy the Earth absorbs per square meter, and then figure out how much it emits per square meter, and then we can use the second number to calculate the temperature. First, we need to know how much total energy from the sun hits the planet. At our distance from the sun, the solar energy fluxes by at a rate of about 1367 watts per square meter. That number goes up or down a little at any given time, but not much. Now, you get 1367 watts per square meter at the top of the atmosphere if your angle is perpendicular to the incoming radiation, but of course the Earth is round, so most places are going to get less than that. If we wanted to impress Professor Alexander, we could figure out the total energy hitting at each point on the sphere using a little trigonometry, and then add it all up using calculus, but oh man, there has to be an easier way. Luckily, there is. Let's assume we're at a point in space behind the Earth. We could look at the Earth and ask how much energy is being blocked by that planet. Well, the entire spherical Earth blocks just a circle of the energy that fluxes past it, a circle with the same radius as the sphere. Once we realize that, we can just calculate the area of the circle to find out how much solar radiation hits the Earth. That's easy. We all remember that the area of a circle is pi r squared. Well, to be precise, we remember that pi r squared is an equation for something. Well, this is it. R is just the radius of the Earth, which we could look up on Wikipedia, but unlike my students, I'm absolutely convinced that I will make fewer errors if I keep things as variables as long as possible and only convert them into numerical values when I've first tried everything I can to simplify. That way, I may do more algebra, but a lot less arithmetic, and my answers will be more flexible for use in other situations. Okay, so now let's zoom in and draw a picture. We're going to call 1367 watts per square meter E sub t for the energy at the top of the atmosphere. Not all of that energy gets absorbed, however. Some gets reflected or refracted away. If you imagine a picture of Earth, you'll see a lot of white swirling clouds in your mind's eye, blue oceans, green continents. All of that is reflected light. We can measure the albedo of the Earth pretty easily. It turns out to be, on average, 0.3, meaning 30% of the sunlight that hits the planet does not get absorbed. We can write that bounced off energy as B times E sub t, where B is 0.3. I'm using B for albedo rather than A because we're going to want to use A for atmosphere, and things are going to get confusing if we're not careful. So you can think of it as albedo, or you can imagine that B stands for bounce. Okay, great. So total energy absorbed by the planet is just E sub t times 1 minus B times pi r squared. It's 1 minus B because everything that doesn't get bounced away gets absorbed. Now, let's figure out emitted energy. Because it absorbs energy, the planet will warm up, and so it will then emit energy. We'll call that E sub s, and to be able to plug it into the Stefan-Boltzmann equation, that'll be the energy emitted per square meter of the surface. I'm drawing it as a squiggly line to clarify that it's long wave rather than short wave radiation. But then remember that the whole Earth emits radiation, not just a flat slice like for absorption, so we need the surface area of the Earth. The equation for the surface area of a sphere is, implausibly, 4 times pi r squared. In other words, it takes exactly 4 circles to cover the surface area of a sphere with the same radius as a circle, though you'd have to cut them up very carefully to make them fit. Then we have total energy emitted equals E sub s times 4 pi r squared. But we also know that the total energy emitted equals the total energy absorbed, so we can write E sub s times 4 pi r squared equals E sub t times 1 minus b times 4 pi r squared. We can divide both sides by 4 pi r squared to get rid of that term, and now I'm really glad we didn't just plug in numbers for our variables back when we first saw that our equation involved r. Anyway, E sub s equals E sub t times 1 minus b divided by 4, which is the same as 1367 times 1 minus 0.3 divided by 4, which is 239.2 watts per square meter. Even better, we can calculate the planet's temperature using the value T sub s equals the fourth root of E sub s over sigma, which is equal to 239.2 divided by 5.67 times 10 to the minus 8ths, the whole thing raised to the quarter power, which is equal to 255 K. Well, crap, that's like minus 18 degrees Celsius, which isn't at all the right answer. The average surface temperature is closer to plus 15 degrees Celsius, or 60 Fahrenheit. But here's an interesting question. What is the planet's temperature if measured from space? 255 Kelvin? No way! Our calculation was spot on. Just by thinking about the situation and plugging in some measurable numbers, we got the right answer. That's kind of exciting. The thing was that we were calculating the temperature of the planet, not the temperature of the surface. And the surface is below an atmosphere. So, let's add the next level of complexity to make the model a little more realistic. Let's just ask, what would the temperature of the surface be if the atmosphere were made up of a single infinitesimally thin layer of a perfect greenhouse gas? By perfect greenhouse gas, I mean that, like carbon dioxide, it does not absorb incoming solar radiation because the energy of those photons is too high. We're calling solar radiation shortwave radiation because it has a high energy and so short wavelength. At the same time, a perfect greenhouse gas would absorb all of the incoming infrared radiation, the long-wave radiation. There's one more thing that we need to know about the atmosphere, and that is that it's very, very close to the surface, even though it doesn't feel that way. 90% of the atmosphere is 10 miles or less above the surface, but the diameter of the Earth is almost 2,000 miles. Imagine that you had a globe in your living room that had a diameter of 1.5 feet. The relative thickness of the atmosphere in that case would be 2/100ths of an inch. That would be the thickness of a few pieces of paper on the globe. The atmosphere is extremely thin compared to the curvature of the planet. Wouldn't it been great if I had drawn some pictures to go with this piece of the discussion? Anyway, this is important because it means that if we zoom in on our model, the Earth is essentially flat at the scale where we see a distinction between the surface and the atmosphere. So we're going to draw our model as if we're looking at a plane, which will matter in a sec. So now we have everything we need to draw a new model diagram. We have the surface and then a thin layer of atmosphere above it. Sunlight hits at the top of the atmosphere, and let's assume that all of the albedo happens at the top of the atmosphere. It doesn't actually matter in the model because reflected light doesn't interact with the atmosphere, so it won't change the results if it bounces off the atmosphere or off the surface. But the truth is that most of the albedo does occur above the surface, and it will definitely make the algebra easier. Now we're going to draw a bunch of arrows, and then we'll be able to write equations just by counting up the arrows at every layer. So we have E sub t over 4 coming in, where the 1/4 comes from the fact that this is the average energy hitting a unit of area, and we learned above that it's 1/4 of the incident area, with E sub t over 4 times b bouncing off, and E sub t over 4 times 1 minus b making it through. All of that energy gets absorbed by the surface, so that is the end of our shortwave line. Now, the Earth is going to heat up. I don't know how much it's going to heat up, but I know that it'll have a temperature, and so it's going to radiate energy. We'll just call it E sub s. And that energy is going to go upward toward the atmosphere. I'm going to draw that as a wavy line, again, to indicate shortwave. We set as an assumption that all long wave radiation will get absorbed by the atmosphere, and that will cause the atmosphere to heat up. So then the atmosphere itself will radiate energy because it will have a temperature. That energy is going to go outward from each molecule in the atmosphere, equally in every direction. So some goes up, some goes down, some goes to the side, and so on. The key insight here is that because the atmosphere is essentially flat, however much goes up and out into space, that same amount will go down toward the surface. So I don't know how much energy that's going to be, but we'll call it E sub a for energy of the atmosphere. We'll draw that as one arrow going down, representing all of the energy in that direction, and one arrow going up, representing the energy going out into space. Now, at each layer, the amount coming in has to be equal to the amount going out. If that weren't true, then down below that layer, things would be either freezing or blowing up. What this means is that I can write the following equations. E sub t divided by 4 equals b times E sub t divided by 4 plus E sub a, that's what's going in at the top of the atmosphere, equals what's coming out at the top of the atmosphere. E sub s equals 1 minus b E sub t over 4, that's what's coming in, plus E sub a is also coming in. We want to get E sub s in terms of E sub t because we know E sub t, so we'll need to substitute away the E sub a. We can rearrange the first equation to get E sub a equals E sub t divided by 4 minus b times E sub t divided by 4, and then we factor out E sub t divided by 4, and we have E sub a equals E sub t divided by 4 times 1 minus b. We can now substitute this in for E sub a, and we get E sub s equals 1 minus b times E sub t divided by 4 plus 1 minus b times E sub t divided by 4. Well, that's just 2 times 1 minus b times E sub t divided by 4. Finally, we can substitute that into the Stefan-Boltzmann equation, plug in values for E sub t, b, and the constant to get T equals 303 Kelvin, which is 30 degrees Celsius. Well, now we've overshot that surface temperature of the planet, but we've learned something critical. We've learned that if you have an atmosphere that is transparent to incoming shortwave radiation, but not transparent to long-wave radiation, then you will warm the surface above the temperature that it would have been without the atmosphere. And that is how greenhouse gases work.